Okay, this is video number 9. It should be watched on Monday the 21st, and I'm going to introduce vector spaces. So here, just throw a definition out there. A vector space is a non-empty set cap V of objects called vectors on which we define two operations: addition and multiplication by scalars. Okay. And the following 10 axioms must hold for vectors u, v, and w, and scalars c and d, which are just real numbers. Actually, I shouldn't say that. Just scalars. They might be real, they might be imaginary, they might be something else, but they're scalars. Okay? Now here are the 10 axioms. Closure under addition. So if vectors u and v are elements of v, then u plus v must also be an element of the vector space V. 2. U plus V equals U plus V equals V plus U. Associativity under addition. And then we have U plus V plus W equals U plus V plus W. All this has to be true. 4, there must be a 0 vector in V so that if you take this vector and add it to U, you identify U. So this is the additive identity. What are we up to? 5. For each, here, let me clean this up. For every, for every U in V minus U must be in V. So that U plus minus U equals the 0 vector. 6. For every C, here, for every scalar C, Cu must be in V. So we have closure under scalar multiplication. Oops. 7. And scalars distribute. So if I take a scalar c and multiply it by the sum u plus v, I get cu plus cv. 8. And if I have two scalars, c and d, and I add them together and multiply by u, I get I get cu plus du. 9, wait, how do you do 9? I forget. I think 9 goes like this. Yeah, that's right. 9 goes 1x. 9, if I have a constant or a scalar times a vector, this is the scalar times the vector, and 10. 1 times u is u, so we have a multiplicative identity. Okay, so that makes a vector space. All 10 axioms have to hold. So if I give you an example, you have to show all 10 to show that it's a vector space. But being good mathematicians, will probably figure out a way to do it much cleaner. So examples. The premier examples of vector spaces are all the Rn's for n bigger than or equal to 1, right? So we've been working with a vector space all along, the premier example, but I don't want you to think that that's the only thing, because the vector space contains objects, which we call vectors. Now in Rn, the vectors are vectors, as we've been defining them so far, but as you'll see, there are other ways to define these objects. And this is my favorite example, right, of a vector space, which we'll work with eventually. The set P sub n of polynomials of degree at most n, which are polynomials of the form p sub t, that's the vector, is a naught plus a1t plus a(n) t to the n, right? So this is the vector. This is the object in the vector. And in this case, the a's are, this is a real polynomials. Okay, the a's are real numbers. And yeah, this is a vector space. And let's just think about a few of these axioms. So one, let's let P sub t and Q sub t, here, let me be official. Come on. Let P sub t and Q sub t be elements of Pn, right? So then P is the vector I have defined above. And Q, I'll define to be the vector, this guy, with the B's. And remember from Math 100, the these coefficients can have a bunch of zeros in them. In fact, they can all be zero. And so, all right, P is so this guy is in Pn, and this guy is in Pn. And if you take P plus Q, you get A naught plus B naught plus A1 plus B1T plus dot 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 AN plus BN T to the N. And so, you know, this is a real number because reals are closed under addition. This is a real number since reals are closed under addition. And all of these coefficients are real numbers closed under addition. So P plus Q is also an element of P sub n. And we've shown closure under addition of vectors. Okay. So that's pretty cool. And yeah, I love this this particular example, and we'll find a way to I always find a way to melt it into the course at some point. Okay, and so now we're going to go back to a definition we've been using, but now it's going to be for any vector space and not just Rn. A subspace of a vector space V has these three properties. So 1, the zero vector in V implies the zero vector is in H, where H is, I should have defined that, H is the subspace of V. So subspace H of V has three properties. Okay. So 0 must be in the subspace. B must have closure in H, not just in V. You automatically have closure in V, but for a subspace you need to show you have closure in H. So if U and V are vectors of H, which is a subset of V, then U plus V must also be in H. So it has to be closed under addition, and C, it's closed under multiplication by scalars. So if U1 is an element of H, then CU1 must be an element of H for scalar C. Okay. And it's always fun to have the easiest example possible. If you let the zero vector be the subspace H, it's a subspace. Zero is clearly in there. It's the only thing. 0 plus 0 is 0. That's in there. And C times 0 equals 0, which is in H for all C, so it's in there. So you've shown all three for that guy. Okay, let's do another example. Oops, not that. Here we go. So the question is R2 a subspace of R3? Right? You think, well, one's smaller than the other, so it's going to fit inside of it. But the problem here is that R2 is not even a subset of R3, right? So the first thing you say about the subspace is that whatever it is, it needs to be a subset of V. So it's got to be vectors in V, and vectors in R2 are not in R3. Now, here's where it gets fun. If you consider the set H which is generated by this one vector. Right? So you take S and T, which are all the numbers in R, and you identify this. So this is a subset of R3. And the question is H a subspace? Of R3. It kind of acts like R2, so you might think, oh, maybe it is. And the answer is yes. And this is one of the ones where I think your author. Oh no, he doesn't. I thought he said it's left as an exercise, but okay. So 1. Let S equal T equals 0. Then 0, 0, 0 is in H. So the 0 vector is in H. So if you take U1 and call it S1 T1 0 and add it to U2, which is S2 T2 0, you get S1 plus S2 T1 plus T2 0, and that's an H because real numbers are closed under addition. Easy enough. I'll leave the third one to you. Okay. Good times. As soon as I saw PN, I got really excited. Okay, so here's our first theorem. This is one that's easy to screw up, but so if V1 down to VP are vectors in some vector space, then the span of these vectors is a subspace of V. And it's called the subspace generated by V1 down to VP. I have a couple of homework problems for you to sort of fiddle around with this, because it can be a bit confusing, but fun. And so that's our intro to vector spaces and subspaces. I'm not going to assign homework until I finish the next video. I guess I could. I'll assign some in class when I see you guys, or post it somewhere. But for now, I'm not really sure what to ask you, except for the ones about spanning. So there we go.